Let's take a look at Lesson 2.5, Take a Guess. This is found on page 211, and this section deals with estimation and number sense. Towards the bottom, number 1 says, write a brief description of 2 or 3 problems that you've had to solve outside of school. What are some problems that you've encountered that aren't school-related? Budgeting, which job to take, when to find time to do homework, which classes should I take, when should I go back to school, which daycare provider should I use, where should I go for dinner, what should I make for dinner? Lots of questions, lots of problems that we encounter every day. Turn to page 212. What are some methods you use to solve problems in your life? Do you think that they apply to solving problems in college classes? What are some things you do when you have a problem to solve? For budgeting, you might make a list. You might write down all the information you have, what money's coming in, what money's going out. For restaurants, you might choose pros and cons. You might write it up on a slip of paper and put them in a hat. Do you think these apply to solving problems in college classes? Some of them can. Well, now we're now well into the second unit of this course. So what is it really about? Math would be the easy answer, but we're sure hoping you've recognized by now that this is not the typical math course. A better answer to that question would be problem solving. Hopefully you've noticed that we haven't done any abstract math. Every topic we've covered here has been an attempt to solve some problem. So by now you've gotten some pretty good experience in solving problems. And without even thinking about it, we've carved out some general guidelines for attacking problems. A Hungarian mathematician named George Polya published a book on problem solving in 1945. In it, he described a problem-solving procedure that he felt was common to most of history's great thinkers. His book has been translated into at least 17 languages and is still a big seller on Amazon, so he must have been onto something. Polya's procedure isn't exactly earth-shattering. Its brilliance really lies in its simplicity. Polya's basic steps are listed in the box below, followed by our spin on each step. Looking at the box, Polya's 4-step procedure for solving problems. Step 1 is to understand the problem. To do this, we write down relevant information. We might draw a picture if there's a picture associated with it. We read through the problem. We just get familiar with it. We don't try to jump right into solving the problem. Step 2 now, we get to devise a plan to solve the problem. We can write an equation. We can pick variables. We can start doing calculations. Step 3 then is to finally carry out the plan to solve the problem. Actually do the work. Step 4 is a very important one, and that's to check your answer. In any problem-solving situation, you should always check your final answer. Make sure it makes sense. Does it answer the question that was asked? One really nice way to help check your answers is to give it a label. You've been solving a problem and you got an answer of -2. And then you put the label of people on it. You've now got -2 people. That answer makes no sense and we have an issue. It would probably make you want to go back and check your work and see if you did something wrong somewhere in the process. Estimation is a valuable skill when it comes to reading information from charts and graphs. In fact, we've used this already in Unit 1. For example, when reading a bar graph, if the length of a bar falls between 2 lines, we have to estimate its height. We can practice this skill by looking at number lines. This number line is a timeline of important advances in medical science. We're going to use this on questions 3 through 10. So get yourself familiar with the number line, kind of get an idea of what years. We're looking from 1500 to 2100, which obviously we're not at yet. A lot of discoveries between late 1800s and current times. Get comfortable with it. You could ask yourself some questions about it. We are going to ask ourselves some questions on page 213. Estimate the year that the microscope was invented and describe how you got your answer. Looking at your chart, you'll see that microscope invented. Let's see if I can get the highlighters to work. I can never get the highlighter to work. Keep trying and it keeps not working. All right, we'll go back to the pen. Microscope invented is right here. Certainly before 1600. About how much before 1600 do you think it is? I would guess maybe 10 years, maybe 15. I think 1590 is a good estimate. anywhere in that ballpark is a sufficient answer. It doesn't have to be exactly the same as mine. It just needs to be close. Looking ahead to number 4, estimate the year that germs were identified as the cause of disease and describe how we got our answer. So let's go back and find germs. Germs identified as the cause of disease. What are the little marks that aren't marked? We have 1800, we have 1900. What is this mark in the middle here? Should be 1850. And we see that germs were identified as cause of disease a little after that. Let's say maybe 1875 or so, 1860. Again, if you're in the same ballpark, we're good. So let's say 1865, split the middle. Again, if you said 1860, if you said 1870, you're in the right ballpark. Which happened first, the first test tube baby or the first heart transplant? Let's go back up here. Here's heart transplant. We'll do that in orange. Test tube baby. They're pretty close. Remember that this is about 1950. So the first heart transplant looks to be almost exactly in between 1950 and 2000, which would be the year 1975. So the heart transplant is probably somewhere around 1975. The test tube baby is close to that. That's my teal circle there. But a little after, maybe 1980. Again, if you're in the same ballpark, oops, I wrote that in the wrong place. So which one happened first? The first heart transplant. So do make sure your heart transplant year is before your test tube baby year. It'd be interesting later to Google these and see how close we were. Which happened first, organs grown from stem cells or the identification of HIV? So let's do stem cells first. Organs grown from stem cells and HIV identified. So HIV is after the test tube baby, which we called 1980. I would say HIV then is probably, let's say 1985. Organs grown from stem cells, which was my light blue one, is after 2000, maybe 2005. Again, we're estimating. Which one happened first? Identification of HIV. Again, if you're in the same ballpark, if you have 2010 here, if you have 1980 here, we're close. It's an estimation. Again, I think it'd be interesting to Google later and see how close we were, what the actual years were. This box here is valuable because it gives us some ways of comparing numbers. These are some symbols you have seen already in this course and some that you'll see more of. First one is equal. That means they're exactly the same. This one is approximately equal to. It's like a squiggly equals. It means they're close but not exactly the same. An equals sign with a line through it means not equal to. This one is read as less than. 10 is less than 12. This one is read as less than or equal to. That's what the line underneath does. This one is read as greater than. 10 is greater than 6. And this one is read as greater than or equal to. Let's go to page 214. Answer some more questions. It says, use your answer from question 5 to write an inequality. So let's go back and see what we had in question 5. In question 5, we said 1975 was earlier than 1980. So 1975 is less than 1980. They want us to do the same thing with question 6, but they want to know which one's bigger or later. We said 2005 was greater than 1985. Question number 9 asks us to look at the two most recent events on the timeline. Organs grown from stem cells and skin cells grown into stem cells. How did the two dates compare? So going back up here, the last two events. Look at how close they are. They could almost be the same year. I'd say they're a couple years apart. So how do we answer this question? How do the dates compare? They're very, very close. Let's see what he says for his answer. Yeah, they're very close, but it's hard to be exact. Now let's practice doing this on a bar graph. On page 215, they give us a bar graph. They show us the cost of homeowners insurance for Arizona, California, Florida, Hawaii, and Texas. The state is across the bottom. The cost per month is on the y-axis. Estimate the monthly cost of homeowners insurance in California. Well, here's California. It looks like it's just slightly above the $80 bar. So we could probably say about $80. If we say about 80, do you think our estimate is too high or too low? I think the bar looks like it goes a little above 80, so I'm going to say we're probably a little bit too low because it appears that the bar goes a little bit above 80. Using your answers, this is number 13 to 11 and 12, write an inequality using greater than or equal to or less than or equal to that describes the homeowners insurance in California. So I would say the cost of homeowners insurance in California is greater than or equal to 80. It's close to 80, but I think it's probably a little bit above. That's why we use the inequality sign. Suppose that you were planning a move to Arizona and wanted to budget a monthly amount for homeowners insurance. Would you prefer to overestimate or underestimate? Anytime it comes to money you're going to spend, you want to overestimate. You'd rather have extra money saved than come up short. So when you talk about spending, always, always, always overestimate. So what estimate would you use for the monthly cost of homeowners insurance in Arizona? Let's go back to our chart. Here's Arizona. Arizona looks to be a little under $60. So if I want to overestimate, I should estimate that it's going to cost me about $60. Probably a little less, but I'd like to go over. On to page 216. Another type of graph we often have to estimate values from is a scatter plot. This one illustrates the federal minimum wage in the United States starting in 1978. If you look at the bottom of my graph, it goes from 1975 to 2010. The minimum wage goes up by $1 increments on the vertical axis. What was the estimate for the minimum wage in 2009? So 2009 is right about here. Comes up to about this point here, which is a little bit above $7. So we might estimate $7.15, $7.20, somewhere around there. Again, this would be an interesting thing to Google and see how close we are. Do you think my estimate may be too high or too low? It could be either. I would guess that I'm a little bit too low, but that's just for mine. If you pick something else, you may say something different. Suppose that a high school graduate in 2009 was trying to figure out how to budget for college while working a minimum wage job. Would she have preferred an underestimate of the minimum wage or an overestimate? If you are trying to estimate how much money is coming in, you want to underestimate. You want to underestimate the amount coming in because you'd rather end up having more and be surprised at the end of the month than not have enough and not be able to pay your bills. All right, just a couple more. This is page 217. We're going to write with some inequalities using the signs that we learned in the previous graph. We can fit at most 12 people on the slow ride pedal bus. So the number of people has to be what? I can fit at most 12 people. I have to fit less than, P is less than or equal to 12. I can fit 12 people. I can put 11, I can put 10, I can put 9. If I bring 13, I've got one person who cannot go. So 12 or below would be okay. It is estimated, number 20, that there are at least 50 ways to leave your lover. So the number of ways is greater than or equal to 50. At least 50 ways, meaning there's 50 or 51 or 52 or 53. You get the idea. Number 21, I get a text alert from my bank if the balance in my checking account drops below $100. So if my balance is less than $100, I get notifications when my daughter's drops below 100. I get notifications every day. The very last one that we're going to do together says that any amendment to the U.S. Constitution will only be enacted if more than 37 states vote to accept it. So the number of states has to be greater than 37. So what's a possible number that could vote for it and get it an amendment enacted? Would 37 work? No, it wouldn't be enough. We have to have 38, 39, 40. So it has to be more than 37. At this point, you should be ready to work on the group work, starting on page 217 and going through page 219.